Okay, so that was a long story about this issue of detecting whether a rotation angle is medium. And you might say, wow, it's a real tangent because what are we trying to do? We're trying to do this. Should I say what this is? This is like 1% error rotation estimation. And it was assuming that the angle was between 0 and 30 degrees. You might say, wow, we spent a long time trying to detect if it's medium, but like we're already assuming that it's smaller than 30 degrees. Well, this is where the pieces are going to come together. Right. And as I said, we're going to just start out by trying to get like factor 2 error. So good. So now let's do the binary search. Here's how the binary search is going to work. So the point is that the idea is, okay, theta starts out as some small number. What we're going to do is basically double theta and see if it's medium. And if not, we'll double it again and see if it's medium. And if not, we'll double it again and see if it's medium. And we'll keep doubling it. We'll see how in a second until we're like, now it's medium. And then, we'll see how many times we doubled it. And that many times of doubling got it up to between 30 and 60 degrees. So now we basically know what theta was up to a factor of 2. That's the plan. Okay, so I'm going to call this new algorithm factor 2 estimate. And it'll also sort of take as input a quantum rotation instruction called mystery rotate. And it's pretty easy. It's just what I said for, I'll say capital K equals 1, 2, 4, 8, 16, etc. So just keep doubling capital K. If is medium. And now I'm going to pass in, I'll use the mathematician's notation, mystery wrought to the power of K. I'll explain what I mean here in a second. Then return the phrase theta hat is 45 degrees divided by K, or I don't know, pi over 4K. Now I'm going to erase is medium because we analyzed it and we remembered its property. So that's good. And the main thing I haven't explained here is what is this mystery rotation to the power of K? I'll just tell you, it means the other subroutine that does mystery rotation K times in a row. So I guess this is like matrix notation. Like if you think of this as like an operation, like a unitary, like we're just doing it K times consecutively. So it's written like that, but let me write it. So, okay, so mystery wrought to the K refers to a new subroutine. But the factor 2 estimate algorithm makes itself out of the subroutine that it's given. Namely, running mystery wrought K times in a row. Okay. So this new subroutine, mystery wrought to the K, it's also a rotation by angle K times theta. Okay, because mystery wrought rotates by theta, you do it K times in a row, you rotate by K times theta. And, the work that we're eventually doing is like how many times mystery wrought gets called. And, okay, if you run it K times in a row, that takes K times. So an important thing to remember is that like calling mystery wrought to the K one time is equivalent to calling just the input mystery rot k times. So this is for the purposes of like counting work. Like every time we do this, we're like, oh, we have to charge ourselves k calls to mystery rot. And the other thing I won't write, but like here, like we're applying is medium to this mystery rot to the k. And then I hope you can kind of see that sort of what's going on is we first try to tell, when k is 1, we try to tell if theta is medium, which it's not, because it's less than 30. Although this might still return yes, because if theta, the initial theta is 29 degrees, that's medium-ish, so it might return yes. But anyway, probably theta is really small, and so now we try to see if 2 theta is medium, and then 4 theta, and 8 theta, and 16 theta, and we keep going until we find that k times theta is medium, which is kind of like saying k times theta is roughly around 45 degrees. And then we're like, okay, cool. So then theta, our guess at theta is 45 degrees divided by k. So hopefully that makes sense to you, but let's, do things carefully. So we're going to do the analysis of this factor 2 estimate algorithm. Okay, so analysis of factor 2 estimate. Okay, so kind of there's sort of 2 things to check. Okay, one thing to check is that if it ever returns, then what it returns is correct. And the other thing is that it does at some point return. Okay, so part 1 of what we need to check, if the algorithm ever returns, then indeed theta hat that returns is within a factor 2 of theta. And part 2 is that it does return. It doesn't run forever. Okay. So let's try to prove these things. Okay, so for part 1, let's say it returns. Then why did it return? It's because it just said yes to some is medium call. It just got yes on some call to is medium mystery rot. Okay. For some value of k, which is a power of 2. And from here, with our full reliability assumption, we know that that means for sure the angle is medium-ish. So therefore, k times theta, which is the angle of this thing, is for sure medium-ish. Okay, so that means between 22.5 degrees and 67.5 degrees. And this is within factor 2 of 45 degrees. Actually, it's a little bit better, right? 22.5 is exactly within factor 2 of 45 degrees. This one is like within 50% of this one. But anyway, it's within factor 2 of 45 degrees. And therefore, the thing that returns theta hat, which is 45 degrees divided by k, is, as desired, within factor 2 of theta. Okay, because that was k theta, that's within factor 2 of 45 degrees. Okay, so that's part 1. Let's do part 2 over here. Hopefully you can see. Part 2. So why does it eventually return? Well, you see it keeps testing. So theta initially starts out less than 30 degrees. That was our assumption. And then effectively, like, we keep doubling it and trying to check if it's between 30 and 60 degrees. And there's exactly factor 2 between 30 and 60 degrees. So if you take a number that's less than 30 degrees and keep doubling it, there's like a unique time when it gets between 30 and 60 degrees. Okay, so yeah, there is a unique power of 2. We'll call it k star, such that k star times theta really is medium between 30 and 60 degrees. And then if and when the factor 2 estimate algorithm reaches this k star in its loop, we know that by this fact, that is medium will return yes for sure. Because if it were to say no, then it would be for sure not medium. So when it reaches this k star, is medium for sure says yes. And therefore, like, factor 2 estimate does indeed halt or return at this point. Okay, and I said like if/when here because actually there's some chance that like right on the just preceding stage, k times theta didn't get all the way up to medium, but it got like pretty close. It got to like maybe 29 degrees or 23 degrees. And in that case, well, at least if we weren't worrying about this temporary pretending, but in that case, is medium, I guess actually even with this, is medium might return yes, but that's okay. I mean, it's fine. We just want to say that like definitely by the time it gets to k star, it'll halt by then. Okay, any questions? Yeah. We're temporarily pretending that. We'll come back to that. The reason I'm temporarily pretending that is I think it makes understanding this argument, part 1 and part 2, clearer. We don't have to worry about like, oh, there's some chance that these, when we call this, it makes an error. Like if we just pretend for a second that it's correct, then I think the analysis makes sense. Yep. Good. So indeed, I'm just going to talk about this runtime now. And indeed, you will notice that if theta were 0, which I assumed it's not, but if it were, then this would be like an infinite loop. I mean, I suppose this statement would not be correct if theta were 0. There would be no such k star. And indeed, as you say, if theta is real small, then this is going to take a real long time. And that's actually inevitable, and it is in here. I mean, if theta is real small, then this reciprocal is real large. Now, in practical purposes, at some point, you'll eventually cut this off and be like, I'm calling it a day. I'm stopping here. And in some sense, I'll go over this. But like, if you finally stop when k is 1,000,000 or whatever 2 to the 20 is, and you still haven't gotten this, at least you basically know that theta is smaller than 1 in 1,000,000 or 30 degrees over 1,000,000. So we'll make that observation also later. But for now, let's just revel in the fact that like we've sort of proven that factor 2 estimate is a correct algorithm for what it is. And the last thing we want to check is like what's its running time, or the number of, not running time, but basically the number of calls it makes to the thing it's trying to estimate, which is basically like running time. So the number of calls to mystery rot is, and actually this is a bit funny, like we're doing something here that we don't often do in algorithmic analysis, which is like understand how the running time, like the running time is going to be a function of the parameter. Like we're not going to say in advance, oh, the number of calls is at most blah. The number of calls is just ends up being like one, like something like 1 over the angle, where the angle is the input. So we know from part 2 that it definitely halts by the k star iteration of the loop. And we know that k star times theta, I mean, the nature of k star is it's the k star such that k star times theta is medium. So in particular, that means k star times theta is at most 60 degrees. And so that means k is at most 60 degrees over theta. I don't know what 60 degrees is in radians, but anyway, this is order 1 over theta. Sorry, that should say k star. So this is just saying the final value of k star is upper bounded by basically 1 over theta. But now every time we do this, this means this is actually 100 times k calls to mystery rot. Right, because mystery rot to the power of k means doing mystery rot k times. And if you remember is medium, I erased it, but is medium like calls its function 100 times. So this costs you 100k calls to mystery rot. Okay, I'm going to eventually say, well, 100 is a constant. That's big O of, but we'll keep the 100 for now. So the total number of calls to mystery rot is, well, it's like 100 times 2 plus 100 times 4 plus 100 times 8 plus ... plus at most 100 times k square or k star. Maybe it'll stop one round before k star, but it's at most this. Okay, and we can factor out the 100. And this is, well, like 2 plus 4 plus 8 plus ... plus k star. K star is some power of 2. And you know, if you like add up all the powers of 2, the result is like 1 less than the next power of 2. So this thing, well, we didn't even include 1, but whatever. Or should we have included 1? Maybe we should have included 1. Yeah, I guess I used 1 here. So, okay, this should have been 100 times 1 plus, and we have a 1 plus. But anyway, this adds up basically to the next power of 2. So this is less than 100 times the next power of 2, which is 2k star. Sorry if it's getting a little bit low. That's order k star. And k star is 1 over theta. So it's kind of funny. It's sort of like your cost is exponentially increasing. And therefore, somehow only the final step really matters to the cost. That's sort of what happened here. Yeah, so as desired, that's exactly this. And in fact, we basically proved this up to a couple of loose ends. So I'll write this over here. We basically did it. By which I mean this, except for a couple of things. Well, 1, we got factor 2 instead of 1%. Okay, we were supposed to get an estimate theta like that was within 1% of, sorry, we're supposed to get an estimate theta hat, which is within 1% of theta. We got an estimate that's within factor 2 of theta. So pretty good, but we'll make it a little bit better later. And there's also this temporary pretend about the reliability. Okay, any questions? Let me actually add, there's one more loose end. There's like a lot of loose ends now, but we saw the main idea. This is the main idea, which I hope you remember. There's some loose ends. Another loose end just brought up is what about theta is 0? What's going on there? And there's another loose end, which is like, oh, we should really tie this back into like Grover and Sats, but we'll do that next time. Okay. Let's also determine if we're going to have a prize today. Now it's 1 in 6 today, but I have a good feeling about this. I went to the Penguins game last night, and they lost in heartbreaking fashion in the last minute. So I got all the bad luck out of my system, and we're going to try to get a 6 today. So 1 in 6 chance. So are we ready? Here we go. No practice. This is going to be it. We can do it. Ooh, we got 1. Yeah, I'm still on an unlucky streak, it would seem.